NVIDIA has made one of the silliest mistakes I've ever seen a company at this size make. The bug in question today is NVIDIAscape, which breaks container isolation in the NVIDIA container toolkit. A lot of words today. We'll go into the bug pretty deep and we'll talk about how it all works. To start, this idea of container isolation or tenant isolation is a problem that a company like NVIDIA has to solve. It's very, very difficult, to give them credit, right? The idea is if NVIDIA is selling these boxes that are just full of GPUs, they also have to sell the software to companies that allows cloud service providers, the CSPs, to put software on top of the GPUs to allow them to give out GPUs to their customers, right? Because people use the cloud. One of the solutions to this process is called the NVIDIA Container Toolkit, which is an add-on to Docker that basically allows the container, which is like an isolated VM sort of, it's not a VM, but it's like a VM, the isolated instance that a customer may use to be given the impression that they have an entire GPU at their disposal. And because of the way that this works, they actually may be given an entire GPU, they just don't have access to the rest of the OS's resources. The whole point of a container is to isolate the user mode process in the container from the rest of the OS. If there were, for example, a malicious container, a good CSP, a good cloud host provider, would not allow this container to affect the other containers. Unless, of course, they were exploiting NVIDIAscape, which is the bug in question today. Now, let's be real. You can't stop 0 days from happening, but one thing you can do is defend against them with today's video sponsor, ThreatLocker. ThreatLocker is a zero-trust endpoint protection platform designed around stopping hackers from getting a foothold in your network. Here, we're on a workstation at Big Corp Incorporated LLC, where a user has downloaded a suspicious PowerShell script, and they're about to run it. Not great. Because ThreatLocker knows the baseline of this computer using its learning mode, where it learned what is allowed during a good baseline, ThreatLocker will detect this and block the execution of the script. Someone in the SOC for this network will get an alert and can either deny it or, my favorite feature, allow it with ThreatLocker's ring fencing technology. They can run the script but deny access to other parts of the computer, like the user's files, or even deny internet access to the script. And the SOC even gets the ability to run the script in a sandbox environment to see what it does before they either approve or deny the access. Using my link right here, go check out ThreatLocker, and next time that zero trust comes up at your company, give ThreatLocker a shot. Thanks again, ThreatLocker, for sponsoring this video. Back to the video. So what would happen, for example, if there were a bug in the implementation of the host OS that a container could interact with that would allow you to potentially interact with another container? Well, this bug does just that. The way this works is basically when you're creating a container, right? You are a privileged user that is able to run a container. So let's say in the typical tenant isolation example, meaning you're trying to prevent one host from being able to see the tasks of another host. Let's say container 1 is Coke and container N is Pepsi, and they're both running on the same CSP platform, but you don't want them to see what the other one is doing. One has the secret formula of Coke and the other has a secret formula of Pepsi. Well, the Coke evil hackers, right, are able to run this create container process. And this is exactly what any container SDK should be able to do, because you have to run the container that Coke wants to run on the GPU platform. Maybe they're making AI generated images of Coke bottles, for example, right? Well, the bug here is so crazy simple. It's like baby's first environment hacking, baby's first privilege escalation, right? When you deploy a container to a cloud provider, typically you give the cloud provider a container image, right? And in the Open Container Initiative, which is like kind of the RFC or like the spec for containers that Docker uses, you give it a container image, and the container image not only has like the file system that the container runs on, but also different properties, for example, right? Well, one of the things that the OCI image has is the container environment variables. And one of the environment variables that the NVIDIA Container Toolkit binary will just trust willy-nilly is LD preload. If you've ever done any kind of like Linux hacking, you'll know where I'm going with this. LD preload is this really interesting environment variable that applies to the dynamic linker loader in Linux. When you are writing a program in basically any operating system, there are other functions that you don't write. These are libraries that you import at runtime to do functionality like printf, like reading strings, stuff that you don't want to have to deal with, right? You depend on other libraries. And this program in Linux, the dynamic linker loader, ld.so, is the program program that loads in those libraries at runtime. Now, there is an environment variable that you can set locally called LD preload that tells the linker, hey, before you load any other objects, inject this one first. What this allows you to do is create your own shared object that loads symbols like printf, malloc, and free before actual libc gets ran. What this allows you to do is potentially instrument those functions, maybe have your own version of those functions. Valgrind, actually, the program that checks for memory leaks, is basically an LD preload hook that runs their own custom versions of malloc and free to instrument those functions. So if an attacker is able to control LD preload, they're essentially able to inject their own code. Not a great time. The kind of like permissions or the kind of security architecture of Linux is designed around not trusting another user's environment variables. For example, when you run sudo, the program is setuid, which means that it runs as another user. Well, because it's running as another user, it does not inherently trust the environment variables from that other user. If it did, you could just do LD preload equals my evil shared object and then just run sudo and now you'd become root, right? So inherently, it is by design not allowed or not common for programs to blindly trust the environment variables of other programs, right? But in this case, because the NVIDIA container toolkit binary is loading in a open container image, and it's going to trust the environment variables, all of them in that image, it will also load, if specified, LD preload from that container image, which will allow the evil container, Coke in this example, to run code on the host, right? It'll allow Coke to deploy a container that gets code execution on the host OS. A pretty simple example of why LD preload is like dangerous is, so I have this program here that just basically reads a password from the user and prints it, right? Get password is a function that I did not write. It inherits that function from libc, which is a library that lives somewhere else. And what I can do is I can compile this program and run it, right? Nothing crazy happens here. It's basically just asking for a password and I print it to the screen. But what I can do with LD preload is I can create an evil library, right? I think create this thing called evil preload. And what I do is I write my own version of getPass. So what it does is it uses the dynamic loader to find in libc the next version of getPass, which is the actual one that should be running. And I run that function really. I do the actual functionality of that. And then instead of just returning and doing nothing extra, I take an evil action, right? So what I do is I call the real getPass function, but then I use fopen to open a malicious log and then write that data to the log, right? This is a very simple example, and all I have to do to execute this is do LD preload equals evil preload.so and then run victim. Do my super password, and you'll see if I do cat temp stolen passwords, these are the passwords that got stolen, right? All I'm showing you here is that LD preload allows me to run code in the context of other code. I can preload code that runs first. The reason why this example isn't super sexy is that all of this is happening at the same privilege level, right? Like the loader is running and it is loading this binary at the privilege of me, and then I am running this process also as me. Nothing really like weird is going on here. Like I'm essentially hooking the functionality of getPass. The reason why this matters so much for the NVIDIA container toolkit is that they're allowing the LD preload hook to go into a process at a different context level, at a different privilege level that allows a attacker to do arbitrary things. And instead of hooking getPass, for example, right, they could just do like, oh, and also we'll do system binsh, right, which runs the shell. I'll do GCC, where's the other one right there, boom, and then LD preload. So this drops me into a shell. Now, again, if this were happening in the NVIDIA Container Toolkit scenario, I would be in a shell at the host OS, not in the container, which is absolutely nuts. Obviously, my idea here is just Ubuntu, nothing crazy. But yeah, now obviously, right, this is not a remote code execution. This is not something that like an attacker can do remotely. There is some inherent trust required here where a container has to be executable by a customer on a cloud platform. But this is kind of the future of computing, right? I mean, I think things go off premises into the cloud more and more each year. And this threat model of instead of RCE being the thing, now it's, okay, customers are trusted by default, but what is the interface between the customer and the CSP? Is that attackable? And then if exploited, what does this allow the attacker to do to other customers on that same CSP? And mind you, this is not a new thing, right? This concern about like containers being exploited is a thing that has already happened to NVIDIA in the past. They had a previous bug last year. There was a time of check, time of use vulnerability in the same architecture, the container toolkit, that allowed people basically to put malicious files into a container image, but it was only checking them after it already mounted them. That's the whole point of a time of check, time of use. Basically, the container toolkit binary was checking to see, hey, do you have evil stuff in your image? It would check, and then it would move on. But after it got done moving on, you could just put the evil stuff there, right? This is like a very standard, like race condition, almost primitive in exploitable binaries. And so NVIDIA obviously is aware of this. They put out a CVE for this. He said the container toolkit allows the platforms that have a vulnerability in the hooks that could allow an attacker to escalate privileges, which means they escape from their container into the actual host OS, to do data tampering, so they could potentially interact with the IPC, the interprocess communication between the main Docker daemon and the other client Docker images, as well as information disclosure and denial of service. I don't think, and again, I don't know a ton about the CUDA toolkit and like the container toolkit for NVIDIA, but I'm assuming that these containers are not using like ARM confidential compute. So this data is not like encrypted at runtime, right? Which means that someone sitting on the host OS could introspect into other containers and potentially do information disclosure. So again, this is a big issue if you're running like a cloud deployment of NVIDIA Container Toolkit where multiple customers live on the same hardware and you're nervous that maybe customer A wants to hack into and spy on customer B. This is that threat model, and it's very interesting. So if you are a CSP that's dealing with this, or you have any questions about this, all you have to do is upgrade your software here to these versions that mitigates the CVE, and you're all good. Also, if you want to mitigate it without updating, you can just bypass this compat libhook, which basically disables the imports of libraries inside of the container toolkit. Now, the question I know you're all waiting for me to answer, would Rust have solved this? Obviously no, right? This is not a memory corruption issue. This is basically a threat model issue or like a logic issue in that trusting environment variables in some cases is not an issue, right? But it needs to be a whitelist where only certain environment variables are trusted rather than a blacklist. Because with a blacklist where you specify what things are not allowed, you will inherently make mistakes. You will miss things, and if you miss LD preload like they did in this case, then you're shit out of luck and you're getting code executed on your CSP. So that's it. Anyway, guys, thanks for watching. I appreciate it. If you're new here, hit that sub button, and we'll see you in the next one. Take care. Pretty cute.